Hi, in this video, we are going to continue a course on mechanics for JEE and Olympiads. And we are going to look at a few JEE problems on statics and equilibrium. So in the first video, we had looked at the basic principles of statics, where the total number of forces should be balanced and the total torques also should add up to zero for a body to remain in equilibrium. What we are going to do today is look at a lot of different situations and solve some problems from JEE, which help you understand this concept a little better, right? So I will be doing some problems and I would recommend that you pause the video when you look at the problem and try it yourself before looking at the solution. That is the best way to learn, and you should try it out before you look at the solution. So let's start with the first one. The question says a particle of mass m is moving along a trajectory is moving along a trajectory given by x is equal to x naught plus a cos omega 1 t and y is equal to y naught plus b sine omega 2 t. You have to find the torque acting on the particle, about the origin at time t equals 0. So technically this is not a statics question, but this is a question that I wanted to share just because you need to know how to calculate torques. So here the particle is actually moving and the x is given as a function of time and the y coordinate is also given as a function of time, right? And now we have to find what torque must be acting on the particle as it moves at time t is equal to 0. So if you remember, torque is equal to R cross F. This is the general way to calculate torque. And here you have to find the torque about the origin. So this R vector must be the vector from the origin to the point where the particle is. And the F vector is the force acting on the particle, right? So now the problem is that they have not given us the force, right? So how would you calculate torque without knowing the force? So the idea is that you have to use the fact that x and y are given to figure out the force on the particle. So we can say the r vector of the particle is x I cap plus y j cap. Basically that becomes x naught plus a cos omega 1 t I cap plus y naught plus b sine omega 2 t j cap. This is the r vector for the particle, the position vector for the particle. If you differentiate this, dr by dt gives us the velocity vector. That would be with respect to time, it would be minus a omega 1 sine omega 1 t I cap plus b omega 2 cos omega 2 t j cap. This is the velocity of the particle. And once you have the velocity, we can also find the acceleration of the particle. Why are we finding acceleration? Because Newton's second law will tell us if you have the acceleration, you can find the net force on the particle, right? So let's find the acceleration by doing a derivative of the velocity dv by dt. And if you do dv by dt here, you get basically minus a omega 1 square cos omega 1 t I cap minus b omega 2 square sine omega 2 t j cap. So this is equal to the acceleration vector for the particle. And if you have the acceleration vector, what is the net force? Force vector, the sum of all the forces on the particle must be equal to mass times the acceleration vector, right? So if you multiply this by mass, you'll get the net force acting on the particle at any given moment, right? So let's do it on the next screen. So the net force on the particle will be minus ma omega 1 square cos omega 1 t I cap minus m a omega mb omega 2 square sine omega 2t j cap. This is the net force acting on the particle. And if you figure out the force at time t is equal to 0. We wanted to find the force at time t is equal to 0, right? So what you can say is, at time t is equal to 0, the force acting on the particle would just be minus m a omega 1 square I cap. This term vanishes. So this is the force at t is equal to 0. And now we just have to find the torque of this force about the origin. How do I find the torque? You have to write the r vector. R vector, if you recall, was x naught plus a cos omega 1 t I cap plus y naught plus b sine omega 2 t j cap. But at t is equal to 0, what is the r vector? At t is equal to 0, that would be x naught plus a I cap and plus y naught j cap, right? This is my r vector. So torque at this moment would be basically the r vector cross f vector, right? So you have to do this vector cross product with this vector, right? So you have x naught plus a I cap plus y naught j cap cross product with the force vector minus ma omega 1 squared I cap. Now I cross I is 0 and j cross I will be minus k. So that will be basically minus minus becomes a plus m a y naught omega 1 square plus k cap. This is the required torque. So that is what you are getting. And notice we have found the torque by an indirect calculation. We did not know the force, but because we knew the trajectory, we were able to find the torque. Right? That is an important idea, that sometimes the information might be hidden and you can use Newton's second law to find the force and then find the torque. And notice that we are always doing the torque calculation using the cross product and the vector method, which is the safest way to do it. Let's go to the next problem. This problem was 2019 JEE mains. It says to mop clean a floor, a cleaning machine presses a circular mop of radius r, vertically down with a total force F, capital F, and rotates it with a constant angular velocity, constant omega, about its axis, right? Now they have said if F is distributed uniformly over the mop, and coefficient of friction between the mop and the floor is mu. Friction between mop and floor. Then you have to find the torque applied by the machine on the mop. So think about the question, what is being done? So you have a circular sort of a mop and you are applying a vertical force of F, and the force F was such that it was distributed over the whole mop, right? This is the vertical force, total force F that was applied on the mop. And now you also are going to rotate the mop. You are also rotating the mop with a constant speed omega about its axis, right? Once you are rotating the mop, you have to calculate the torque applied by the machine on the mop, right? And there is friction between the ground. The ground is obviously an XY plane like this, and there is friction between the ground and the mop. The coefficient of friction is mu. So first of all, why do you think there will be a torque on the mop by the machine? Why does there have to be a torque? The reason is, if you rotate the mop with omega angular speed, and if the angular speed is constant, then actually friction will be trying to oppose the rotation, right? Friction at any given moment, friction will oppose the relative motion of the mop across the floor of the across the floor, right? So there should be a torque of friction, torque due to friction. Now, if you had started the rotation of the mop and there was a torque of friction, then the torque of friction would have basically slowed down the mop and the rotation of the mop would have stopped after some time, right? But the machine is ensuring that the mop is constantly rotating with the same angular speed omega, which means that the machine is applying a torque to cancel the torque of the friction. So machine's torque basically cancels the torque of friction, and therefore there is no net torque, and therefore the mop can rotate with constant angular speed, right? So our job is to find the torque applied by the machine on the mop, but we can calculate it indirectly by finding the torque applied by friction on the mop, which tries to slow down the angular velocity of the mop. If you can calculate the torque due to friction on the mop, you can also say that that must be equal to the torque by the machine on the mop, right? I hope you understand what I'm describing here. So how do we calculate the torque by friction on the mop, right? That is what we have to achieve here. So let's think about it. The question had said that the force was applied uniformly over the whole area. So there is a vertical force of F by pi r square, which is per unit area, force per unit area on the mop, right? So this force was balanced by the normal force from the ground, right? And since this force, the vertical force, downward force was distributed over the whole mop, you can also say that the normal force is also distributed over the whole mop. And both the magnitudes should be equals. So what we can say is that there is a normal force N distributed over area of pi r square, over area pi r square vertically upward, right? Now, in order to calculate the total friction and the friction torque, let's take a small ring like this. I have taken a ring like this, which maps, like it has a tiny area. It has some area dA, and therefore it will experience some friction, right? Because it is rotating with speed omega, let's say, it will experience friction which will try to oppose the motion. Friction will try to oppose the rotation everywhere, right? So what we need to calculate is the value of this small friction dF. The small friction dF will be equal to mu times the small normal force on this ring. The ring experiences a small normal force upward. And how do we calculate this normal force? We know that the total normal force N was equal to F by pi r square. Actually, N was equal to F, and F was distributed over the whole ring. So what we can say is N is also similarly distributed over the whole area of the ring. So what is the normal force on this much area? What is this area? Let's say this is small r and this thickness is dr. So the area dA here is 2 pi r dr. So for this much area, the normal force that will be there would be N by pi capital R square multiplied by 2 pi r dr. This is normal force only on this a ring. We are calculating it by saying N by pi r square, which is the normal force per unit area multiplied by the area of the ring. This comes out to be 2n r small r by capital R square dr, right? This is my basically normal force, and n was equal to F, so we can write this dn as 2F small r by capital R square dr, right? And friction force will become mu times this, so 2 mu F small r dr by capital R square. This is the friction force that acts on different portions of this ring, right? Now, what is the torque due to this friction? The small torque would be R cross F, R cross F, and it is technically a dF. So we can, and you can see that the friction is always perpendicular to the R vector. The R vector is radial and this is tangential friction. So we don't have to worry about the cross product so much. This becomes basically 2 mu F R square dr by capital R square. This is the small torque, right? On this ring. If the torque on this ring is this much, you can find the total torque on the whole body by integrating this d tau, and that will become 2 mu F by capital R square comes out an integral of R square dr from 0 to capital R, which basically becomes R cube by 3. So you get 2 mu F R by 3. This is coming out to be the total torque on the whole mop by friction. And obviously this is equal to the torque by the machine on the mop, because only then can the torques be cancelled and constant angular velocity be maintained, right? Okay, so that is the solution for this 2019 JEE mains question. We are balancing torques and getting the answer. But the key point here was to take an elemental ring and then find the small torque on it and then integrate to get the total torque. So I hope you understand that technique. Let's look at the next problem. This is JEE 2002. And the question says a meter scale is balanced on a knife edge at its center when two coins each of mass 10 grams are put one on top of the other at the 10 centimeter mark. The scale is found to be balanced at 40 centimeter. The scale is found to be balanced at the 40 centimeter mark. You have to find the mass of the meter scale. Mass of meter scale is how much? Okay, so again, pretty straightforward question here. Let's look at what is happening here. So earlier, the meter scale was balanced on a knife edge at its center. So this is a meter scale, let's say. This is the center mark, which is 50 centimeter mark, and it was balanced here earlier. Now what you did was you put two coins at the 10 centimeter mark. This is 10 centimeter mark. You put coin 1 and coin 2 here, right? And now the meter scale is balanced at the 40 centimeter mark, not at the 50 centimeter. It is balanced here, 40 centimeter mark, right? So basically what has happened is this 20 grams weight has shifted the equilibrium a little bit, and because of the torque here, now the meter scale is not being balanced here. So earlier, if you think about it, the weight of the meter scale was acting at this point, and the normal force from the knife edge was acting here, and the forces were balanced and the torque was also balanced. because there is no torque about any point because they get cancelled out. There is no torque about this knife edge basically, right? But now what is happening is the fulcrum is here. This is the point where you have to balance torques about, but the weight will still act here, right? The weight of the meter scale still acts at the 50 centimeter mark, and basically you'll calculate the torque of this weight will be turning it like this, and the torque of the 20 grams will be turning it this way, right? So technically, what you can say is that 20 grams times 20 by 1000 times 10, this is mg for the 20 gram thing, times 30 centimeter, 30 by 100, should be equal to whatever is the mass of the scale, m times 10 times 50 by, not 50, the 10 centimeter from here. So 10 centimeter by 100, right? So this becomes, basically all this cancellation happens, and you get 6 by 100, m is equal to 6 by 100, right? So what are we doing basically? We are balancing torques here. This torque due to this weight and the torque due to the weight of the whole scale. And those things got balanced. Mass is coming as 6 by 100. So basically that is 60 grams. So pretty easy question. I just wanted to show you a torque balance question basically. Okay. Let's look at another question like that. This one is JEE 2019. JEE 2019. And the question is like this. There is a figure. There is a vertical line here. And there is a rod like this. And this rod is extended like this also. There is a 90-degree angle here. And this is A, this is B, this is C. And this angle is theta. Now the question is saying an L-shaped object made up of thin rods of uniform mass density. These are thin rods of uniform mass density. Is suspended from a string as shown. Is suspended from a string as shown. If AB is equal to BC, AB is equal to BC, and you have to find tan theta. Right. So AB is equal to BC is given, and you have to find out tan theta. Now here, what we have to think about is there will be mass of this rod which will be acting at its center. There will be mass of this rod which will be acting at its center. Right. Now you have to realize that the whole L-shaped object will never be in equilibrium if the center point here is on the left side of the vertical line. It cannot be in equilibrium like this, right? Because the mass here and the mass here both create similar torques now. Basically, that will make the whole L-shaped object swing like this about this vertical point from where it is hanging. So if you calculate the torque of this mass about this point and torque of this mass about this point, both the torques get added, and therefore it will swing from left to right. Right? So the situation must be such a way that the angle must be actually smaller. And I will redraw the figure a little bit. The angle should be like this. This is one rod and this is one rod. This mass should be on the center of mass of the second rod must be slightly to the other side. Right? This is ABC and this is angle theta. So there is a force mg acting like this, there's a force mg acting like this. We have to calculate and balance the torques due to these two forces. Only if we can balance the two torques will the L-shaped object stay like this in equilibrium, right? So in order to calculate the torque, you can take this whole length as, let's take this whole length as 2L. So this much length is L, right? So torque about A due to this mg force would be basically due to this perpendicular distance. This perpendicular distance is actually L sine theta. L sine theta. So torque about A due to force mg would be mg L sine theta, and this is a clockwise torque, anti-clockwise torque. So this is plus k cap. The direction of the torque is plus k cap. And the next torque will be due to this. And notice this distance. I need the perpendicular distance of this point from the point of application. Basically, I need this much distance, right? So what you can say is that since the overall angle was 90 and this angle was theta, I know this small angle is also theta. So you have L here, and L cos theta is this much. This much is L cos theta. And what is this height? So I will just draw the figure like this. So think about it. This length was 2L. This length is L. If I draw like this is L cos theta because the angle here is theta. But what is this much? Because the angle here is theta, this is 2L sine theta, right? So the gap here, this gap here is basically L cos theta minus 2L sine theta, right? L cos theta minus 2L sine theta is coming out to be the perpendicular distance of this mg force from the vertical line which passes through the axis or which passes through the point of suspension. So the torque due to this would be, in this sense, it would be a clockwise torque. So it will be minus k cap and it will be mg into L cos theta minus 2L sine theta minus k cap. That is my torque due to the second weight, due to the weight of the BC segment. Now these two torques should add up to 0. So we can easily equate it to 0 and we will say basically that mgl will get cancelled everywhere. And you have sine theta minus cos theta plus 2 sine theta is equal to 0. So you have 3 sine theta is equal to cos theta. So tan theta is equal to 1 by 3. So we are getting the value of tan theta as 1 by 3 for the equilibrium of this L-shaped object. So notice how we calculated the torque. That is the key point here. Once you get that idea, after that it is pretty obvious what to do, right? Okay, let's look at a slightly more complicated situation. This question appeared in JEE 2016. So this is question number 5, JEE 2016. A uniform wooden stick of mass 1.6 kg, mass 1.6 kg, length L, rests in an inclined manner, on a smooth vertical wall of height h, smooth vertical wall of height h, H is less than L, such that a small portion of the stick extends beyond the wall. Reaction force of the wall on the stick, is perpendicular to the stick. The stick makes 30-degree angle with the wall and the bottom of the stick is on a rough floor. Bottom of the stick is on a rough floor. Okay. The question has also stated that reaction of wall on stick is equal in magnitude to the reaction of floor on stick. To the reaction of the floor on the stick. We have to find the ratio H by L and friction force F on the bottom of the stick. We have to find the friction force and we also have to find the ratio H by L. This is the question. I want you guys to pause the video and try it out yourself. See the situation, draw a figure, draw all the forces and try this question yourself. And I will solve it on the next screen. So basically, you can pause the video right now and try it out yourself. I will do it on the next screen. So this is like a wall. This is the stick. This height is H. The length of the stick was L, the overall length of the stick. There is reaction here which is perpendicular. So let's say normal force at this point. We will call this as A and this as B. Let's call it at NB. This is perpendicular to the stick. There is NA here, which is perpendicular to the ground. And there will be friction here like this. The stick is resting like this against the wall and the angle that it makes with the wall is 30 degrees. And what we have to say is, we have to find H by L, we have to find friction force. Obviously, there is weight of the stick also. Weight of the stick will act at the midpoint. So basically, this length is L by 2. And this weight will be acting mg like this downwards, right? And the question has told us that Na is equal to Nb. In terms of magnitude, the two forces are equal, right? What we will do now is, for the equilibrium of the stick, we will balance the forces and we'll also balance the torques. So if this angle is 30 and this angle is 90, this angle must be 60. So you have Nb cos 60 upward and Nb sin 60 this way. Right? Great. And we should say that the force equations will be the total vertical force is Na plus Nb cos 60 minus Mg is equal to 0. This is equation 1. The horizontal equation is Nb sin 60 minus friction is equal to 0. This is equation 2. And for the equilibrium, the torque should also be balanced, and we can calculate torque about any point we like. So we'll calculate, let's say, torque about point A, right? There are two forces acting at point A, NA and F. So we don't have to worry about the torques due to them. We'll just calculate the torque due to the remaining forces at point A. So we will get mg's torque would be mg times this distance. This is the perpendicular distance from the line of action of the force to this point. So that will be basically, if this angle is 30, this is 60. So it is L by 2 cos 60. So you will have mg into L by 2 cos 60. This torque is a anti-clockwise torque. And then there will be torque due to the overall force NP, which is perpendicular to the line joining. So we will say that this is, what is the length of this much, right? Notice that it is not L, because it was slightly extended above here. So this height, this length, basically the length AB is going to be H by AB should be equal to sine 60, right? So therefore, H by sine 60 is AB. So therefore, the torque by friction is minus the torque by normal force is minus NB into H by sine 60. And these two torques should also add up to 0. This is the third equation. And the fourth result is NB is equal to NA, which was given to us in the problem itself, right? So if NB is equal to NA, we can calculate everything now. The first equation becomes NA plus NA cos 60 is half minus mg. M was 1.6 kgs, I think. The question had mentioned the weight of the thing. So yeah, 1.6 kg times g. So this is 16 is equal to 0. So you get 3 Na by 2 is equal to 16. Therefore, Na is equal to 32 by 3. We have found Na and we have also found Nb basically. Now friction value can come from here. So we get friction is equal to Nb sine 60. So Na sine 60 sine 60. So that would be 32 by 3 into root 3 by 2. So this is 16 by root 3. So friction value is 16 by root 3. That is one answer. And now from this equation, we should get H by L. So we will simplify it here. Let's rub it off a little bit. What we get is from the torque equation, we end up getting mg L by 2 cos 60 is half is equal to NB H by root 3 by 2, which is sine 60. Mg is 16, L by 4 is equal to NB. NB is equal to Na is equal to 32 by 3. So 32 by 3 H into 2 by root 3, right? So this gets cancelled here and you get 3 root 3 by 16 is equal to H by L. So basically you are getting H by L is 3 root 3 by 16 and Na is equal to Nb is equal to 32 by 3 and also friction force is equal to 16 by root 3. So these are the answers. I wanted to discuss this problem because this type of setup has been asked many times before and you need to be aware of what to do when you encounter this stake against a wall type of setting, right? Let's look at the next problem. This is question number 6 and the question says a ladder of length L and mass M is leaning against a frictionless wall leaning against a frictionless wall, it makes an angle theta with the horizontal. Horizontal. Mu s is static friction coefficient. Static friction coefficient between the ladder and the horizontal surface. Now the question is asking how high from the horizontal surface can a man of mass m climb before the ladder slips? That is the question. It is a similar setting as before. We are just dealing with a special case that the ladder is about to slip here, right? So how high can the man climb before the ladder slips? So I will draw the figure like this. This is the situation. This is angle theta. Ladder is leaning with angle theta. Ladder has length L, mass n, small n. And this is basically the wall. This is a frictionless wall. And let's say the man has come here. Man has climbed here, and let's say this height is h. This height is h. The height is measured from the horizontal. And we are saying that the ladder is about to slip right now, right? The center of mass of the ladder is here, and it exerts a force. There is mg gravitation here. There is capital Mg here, right? Now, there is normal force from the ladder at this point, Nb, let's say, and here there will be Na. And since the ladder wants to slip this way, friction will be acting this way. So friction is acting here, F, right? And mu s is the coefficient of static friction. In order to find the height at which the ladder is just about to slip, we will say that the static friction force is at its maximum or at its upper limit. Right? Friction static is usually less than equal to mu s into Na, but we will take it as equal to mu s into Na because it is just about to slip. Right? Now, writing the same type of equations, the vertical equations, force balancing and torque balancing equations, you will get one equation Na is equal to mg plus capital Mg. These are the two downward gravity forces, right? Right now our system is man plus ladder. Therefore, the two vertical forces are being added, which are downward. And then you will have Nb is equal to Fs. And you will say that Fs will be equal to mu s into Na, right? These are the force equations. Now the torque equation, the torque also must be balanced, right? So the torque equation, let's calculate the torque about the point A, because then two of the forces don't have to be considered. Na and Fs don't have to be considered because they are passing through the point of application of that force. So there is no torque of those two forces about this point A. Torque of the other forces would be basically small mg has a torque of L mg into L by 2 cos theta because this distance is L by 2 cos theta. Now we have to find out what is this distance also till here, right? And you have to realize that the height here is h and theta is the angle. So you can say tan theta would be h by x, right? So x is h by tan theta. So we'll say the force, the torque due to the capital Mg is mg into h by tan theta, right? These two torques are trying to pull the ladder in this way, but the torque due to Nb is trying to turn the ladder in the opposite way. So the two torques must balance when it is just about to slip. Afterwards, it will be unbalanced and it will slip, right? And the torque of Nb is simply Nb into L sine theta, because this length is L and this height is L sine theta, right? So this is my final equation. Now, what you have to do is solve all of these equations to find h. These are the four equations. You have to solve all of them to find h. Obviously, we can eliminate many things, like you can say NB is equal to Fs, and so Fs is mu s Na. So you can say NB is equal to mu s Na, right? So everywhere you can replace NB with mu s Na, and Na is m plus mg. So we get NB is equal to mu s times m plus m into g, right? And now here we will just solve this equation. We only have to put NB and we can find h in terms of the other variables, right? So how do I do that? Let's see. We will write this as capital MGH cot theta plus is equal to NB, which is mu s m plus m g L sine theta minus small mg L cos theta by 2, right? So H is equal to 1 by mg cot theta times mu s m plus m g L sine theta minus g L m cos theta by 2, right? And obviously g gets cancelled throughout. What you get here is now you get a tan theta by capital M. G has gotten cancelled. You get mu s m plus m L sine theta minus L small m cos theta by 2, right? This m can be taken inside and you can rewrite the whole thing by basically taking L sine theta outside, or you can leave the answer here, it's fine. This is the correct expression. The rest of it is just simplification. Notice that we have only the variables that were mentioned in the question are appearing in our answer. Theta was mentioned, L was mentioned, small m, capital M was mentioned in the question, and mu s was mentioned. So ultimately, we are just solving for the known variables, right? So this covers all of these rolling type of questions, and basics of statics and equilibrium we have done. In the next video, we'll continue with the topic, but in the next video, we are going to look at a new type of problem scenario, which is sliding versus toppling. These types of problems you might have seen and you might have struggled with such concepts. We'll cover all of the notions of sliding and toppling in detail in the next set of problems, which will also be derived from JEE questions. So hopefully you will watch that video and figure out those concepts as well. If you like the content, please subscribe to the channel and share it with your friends. Your support is very important for me. So your help in subscribing and growing the channel helps me also get motivated for providing content like this. Uh, this course will continue. The next video will have basically sliding versus toppling problems. The next video after that will have certain more advanced problems on statics, which are slightly more general, and that will conclude the chapter roughly, this section of the course. After that, we'll move on to the next section of the course, which is basically Newton's laws of motion. We'll see what can be done there. That's it for now. I'll see you next time.